When we look at standard machine learning tools like linear regression or naive Bayes, we expect a mathematical equation or a probability tree to hand us a prediction. We expect a model. The k-nearest neighbors algorithm skips that entirely. It operates as an anti-model. It solves problems simply by memorizing past data, and when asked a question, it looks at the closest historical examples to find the answer. This concept was formalized in 1951 by mathematicians Evelyn Fix and Joseph Hodges at UC Berkeley. They were working under a research contract for the U.S. Air Force, tasked with solving complex classification problems without relying on the rigid, traditional computing models of the time. Their solution, a non-parametric classifier, proved so effective that it was kept as a confidential military document for years before the public ever saw it. Today, we call this approach lazy learning. During the training phase, the algorithm does exactly zero processing. It just stores the data. Every ounce of computational work is deferred until the exact moment you ask it to make a prediction. Its true power is that laziness. By refusing to commit to a strict mathematical formula up front, it maintains perfect flexibility, ready to adapt to new data the second it arrives. To see how this works, imagine we have two features, like temperature and humidity, that we use to classify historical days as either rain or no rain. This graphic plots exactly that scenario. We have established violet points for rain, orange points for no rain, and in the center, an unclassified query point. The algorithm's first step is measuring the straight line distance from our query to every single stored point. Then it applies a strict limit on its voting constituency using variable k, the exact number of closest neighbors allowed to influence the decision. Setting k to 3 isolates the 3 closest points. With 2 orange against 1 violet, the majority rules, predicting no rain. But that k parameter is a major vulnerability. If we expand the boundary to look at the 5 closest points instead, we capture a different set of neighbors, and the Democratic vote could easily flip to rain. This voting mechanism is also why, when deciding between two categories, k must always be an odd number. Choosing 3, 5, or 7 permanently eliminates the possibility of a tie. There is no fixed equation here. It is a highly scalable system where altering the size of the voting constituency shifts the boundary of reality. There is, however, a mathematical trap built into this logic. Euclidean distance calculations completely break down if your data features are measured in vastly different units. This table compares a small-scale feature like humidity, measured from 0 to 100, against atmospheric pressure, sitting around 1,000. Because distance is unitless math, pressure's massive numerical range silently dominates the calculation. It drowns out humidity, selecting the wrong neighbor. The mandatory fix is feature scaling. Using standard standardizer, we mathematically squash all features into a proportional range, sharing a mean of 0 and standard deviation of 1. Rescaling converts raw numbers into comparable z-scores, allowing every feature to count equally. Because k-nearest neighbors does not learn any internal weights during training, standardizing your data is not an optional best practice. It is the strict mathematical step that gives every feature equal voting power. When we take this geometric logic out of a simple weather model and apply it to a complex biological dataset, we see why it works. This matrix shows the famous iris dataset, mapping 3 flower species based on the physical measurements of their sepals and petals. The algorithm relies on these traits forming dense clusters. Notice how the red points isolate themselves from the others across all pairs. Close physical proximity in this feature space reliably guarantees the same biological species in the real world. But this accuracy comes with a catch. We mentioned the training phase has 0 computational cost. The bill comes due during the query. To classify a single new flower, the algorithm requires O of n times d time complexity, meaning it must calculate the exact distance to every single stored point across all dimensions. K-nearest neighbors proves that sheer data retention and geometric proximity can bypass predictive modeling entirely. The question modern engineers face is simply how to afford the brute force computing cost required to run it at massive scale.
Storing everything and voting at query time sounds free. The training phase is mathematically instantaneous. Calling fit is an O1 operation because it doesn't solve any equations. It simply dumps an n by d matrix of data straight into memory. But predicting a single new point triggers an exhaustive O of n times d brute force computational sweep. The algorithm has to measure the exact distance from the new query to every single stored point. There is no early exit. The best, average, and worst-case execution times are identical, meaning every connection is blindly recalculated every single time you ask it a question. You can try to optimize this with spatial indexes like KD trees or ball trees to drop that query time closer to O of d log n. But these optimizations are fragile. In many real-world datasets, these structures can degrade, forcing the machine right back into an expensive brute force scan. The algorithm simply defers the entire computational load of machine learning out of the training phase and dumps it directly onto the live query phase. We can see this exact pipeline play out in a real-world classification task, using historical weather records to answer a simple question: will it rain tomorrow? First, the raw CSV file is loaded, and the text categories of yes and no are converted into integers of 1 and 0. Next, the dataset is structurally split, severing the input attributes, the features, away from the target answers, or the labels. Then, train test split explicitly quarantines exactly 20% of the historical data, providing a clean, untouched baseline to evaluate the model's accuracy later. This entire sequence is mandatory data plumbing. It is just organizing the environment so the algorithm has a clean space to touch the numbers. Cautionary. The script's biggest vulnerability sits right in the standard scalar implementation. Look at the raw features table. The massive atmospheric pressure range drowns out humidity values, distorting the distance math. To fix this, the .fit command is executed exclusively on the training set. This calculates a baseline, creating normalized z-scores, where both features count equally. Once that baseline is locked, the .transform function applies the scaling to both sets, ensuring the test data is properly scaled without altering the model's underlying parameters. Fitting the scalar across the entire dataset before splitting is a massive bug, quietly leaking future test answers directly into the training phase. The actual algorithm instantiation happens on a single line, k-neighbors classifier, setting n neighbors to 5. Setting the k parameter to a small, odd number mathematically prevents tiebreakers when forcing the algorithm to choose between two binary classes. The classifier.fit command is the literal embodiment of lazy learning. It solves exactly 0 equations and strictly memorizes the training data. This graphic illustrates where the heavy lifting actually happens inside the classifier.predict function. Distances are calculated, and the nearest neighbors are isolated so they can actively cast their majority vote. The absolute entirety of the classification logic fits gracefully into 4 lines of code, yet those 4 lines trigger a relentless O of n times d search through every record in your database. Every single time that tiny predict script receives a query, the machine is forced to execute a complete, exhausting scan of the entire training archive. That bottleneck runs straight into a fatal mathematical flaw that breaks this algorithm in production: the curse of dimensionality. As you add more descriptive features or dimensions to your dataset, all the data points drift apart. They quickly become nearly equidistant in high-dimensional space, rendering the entire concept of a nearest neighbor mathematically meaningless. So the code is trivial, and the error rate is mathematically guaranteed to stay within twice the optimal limit, which raises the real engineering question: when is this brilliant, and when does it quietly fall apart in production? That is what we settle next. Using this algorithm means accepting an uncompromising trade-off. The entire algorithm relies on a single physical truth. Similar things share a label. It works perfectly when your data naturally forms distinct, separated neighborhoods. If that grouping is clean, you can use those neighborhoods to build recommendation engines, score credit risks, predict tomorrow's weather, or read human handwriting. Look at the empty white space between groups. If a new data point lands here, isolated, it's immediately identified as an anomaly. Before an engineering team spends thousands of hours training a massive, opaque neural network, This algorithm serves as the perfect, transparent baseline to test the quality of the data. It is also non-parametric. That means the model makes zero assumptions about the underlying shape of your data. It can organically bend to fit highly irregular decision boundaries without forcing them into a strict mathematical formula. It natively handles complex, multi-class problems. And if your system ingests new data, you simply drop it into the database. The model updates on the fly without ever triggering a retraining pipeline. This step-by-step visual guide shows the algorithm in action at query time. It is completely interpretable. You can point to the exact historical examples, the 3 nearest neighbors, and watch them vote to predict the unknown query point. You are trading the heavy computational cost of upfront training for total operational transparency. You get an instant, adaptable system with a clear paper trail for every single prediction. But that upfront savings comes with a brutal cost at deployment. To make a single prediction, the algorithm must execute a brute force scan, measuring the distance to every single point in the database. That imposes a massive memory footprint. The entire historical training dataset must remain resident in your system's RAM at all times. Then you run into the curse of dimensionality. Scanning a massive dataset to calculate thousands of distances for every single real-time user request will immediately break a production system's latency budget. It is simply too slow for live environments. This architecture is called lazy learning. This gives us explicit rules for deployment. First red line. If your system requires millisecond-level response times over millions of records, you cannot use this algorithm in its raw form. Second red line. If your feature space is highly sparse or stretches across hundreds of dimensions, you have to aggressively preprocess it, or the algorithm will output garbage. Third red line. If your hardware environment lacks the memory to hold the full training set at once, you must abandon this approach entirely. This infographic illustrates the hidden trap of unscaled features. The algorithm fails in production, not because of flawed underlying math, but because it collides with physical hardware limits and unscaled dimensions. To force this algorithm through the production bottleneck, engineers must shrink the data. Running a dimensionality reduction technique like principal component analysis is mandatory to keep the math functioning. They also adjust the voting rules. By applying inverse distance weighting, the closest neighbors get a heavier vote, which prevents ties and stops the model from washing out local details. This side-by-side comparison diagram shows the bias-variance trade-off when tuning the k parameter. A small k, like 1, gives you a jagged boundary that overfits to background noise, while a large k, like 7, smooths things out to create a robust, generalized boundary. To bypass the exhausting brute force scan, a production-grade implementation integrates the raw algorithm into a hardened pipeline of scaling, reduction, and indexing. Even with its operational quirks, the algorithm proves that our simplest intuition, judging an unknown thing by the company it keeps, can be incredibly rigorous. In fact, the 1967 Cover-Hart theorem guarantees that as your dataset grows, a simple one nearest neighbor rule will never have an error rate worse than twice the optimal possible classifier. This is the cover for 50 algorithms every programmer should know. K nearest neighbors is a foundational technique for modern software design. Find runnable Python code on GitHub and explore more resources at neuralsca. But what if we abandoned physical distance entirely? What if, instead of measuring the space between points, we classified data by asking a ruthless sequence of yes or no questions? That is how we build a decision tree.